Today we're going to talk about continuity. As I said earlier, in previous math classes, if you talked about continuity at all, you probably just talked about it in terms of a graph. If you can draw the whole graph without ever picking up your pencil, then it's a continuous function. So that's not exactly a definition, though, is it? So, and I misspelled continuity. Yikes. Continuity. There's a missing N in there. Continuity at a point. So a function is continuous at a number c if the following three conditions are met. So all three of these have to be met. F of c has to be defined, right? C has to be part of the domain of the function. The limit as x approaches c of f of x has to exist also, and those two have to be the same, right? If you have the first two but not the third, you have a removable discontinuity. If you have, you could have, actually, sometimes people just focus in on this last one because these both have to exist in order for them to be equal. So that's really the most important part, is that the limit as x approaches c of f of x has to be f of c. So let's look at some examples. Let's determine whether f of x is 3x squared plus 5x minus 4 is continuous at x equals 1. Well, let's find f of 1. F of 1 is going to be 4. That's pretty easy to do in your head. And the limit as x approaches 1 of f of x. Now there's nothing crazy going on in this, so it's a polynomial. We just substitute. That's also 4. These are equal. So because those two are equal, f is continuous at x equals 1. Let's look at the next one. Determine whether the function g of x, which is equal to x squared plus 9 over x squared minus 4, is continuous at x equals 2. Well, I always start with the function itself. Does g of 2 even exist? If we substitute in 2, the numerator is 13, that's fine, but the denominator is 0, which is a problem for us. G of 2 does not exist. Therefore, do you guys ever use the 3 dots for therefore? Yeah. Therefore, G is not continuous. At x equals 2. There's a whole bunch of those from set notation. That's the only one I use. There's probably a dozen or more. That one comes up often enough to where I use it all the time. So we say that a function f is continuous on its domain if it is continuous at every number c in its domain. So, depending on the book that you look at, I like saying it this way. I say that it's continuous on its domain. Some textbooks, and it's mathematically speaking true, but it's confusing, will say that a function is a continuous function if it's continuous on every point of its domain. Which means that, for example, tangent, which has an infinite number of vertical asymptotes, is a continuous function because it's continuous everywhere that it's defined. But doesn't feel like a continuous function, does it? So I just say it's continuous on its domain. You could just say that it's continuous. Although, man, you're like, you look at the graph of tangent and you're like, well, that's not continuous. Well, it's continuous everywhere it's defined. So anyway, polynomials and rational functions are both continuous on their domains. So any polynomial function, that's continuous everywhere because polynomial functions are defined everywhere, and rational functions are continuous everywhere that they're defined. So let's take a look at this one. Let's determine if f of x is equal to the square root of x squared plus 4 over x squared minus 4 is continuous at the following 3 points. So we need to look at, starting with -2, f of -2. At -2, what happens with f?
Zero in the denominator.
Yeah, so that's a problem. So this does not exist. Therefore, f is not continuous. At x equals -2. And we might as well do 2 at the same time because it's the same reason. F of 2 doesn't exist. Therefore, f is not continuous at x equals 2. All right, well, let's look at f of 0. F of 0, we're straight up substituting in, is the square root of 2 over -4. And because there's no crazy business going on in this is just the ratio of two things that are nicely continuous, that's going to be equal to the limit as x approaches 2 of f of x. Excuse me, approaches 0. My fault. Therefore, f is continuous at x equals 0. All right, so let's determine whether this function is continuous at x is equal to 3. So, first of all, what is f of 3? 9. It tells you straight up. It's defined that way. Well, if we're going to look at the limit as x approaches 3 of f of x, we need to look both from the left and from the right because it's defined two different ways. So, the limit as x approaches 3 from the left of f of x will be the limit as x approaches 3 from the left of, I'm going to go ahead and factor this, it's x plus 3 times x minus 3 over x minus 3 except at 3, x minus 3 over x minus 3 is equal to 1, so that's going to be equal to 6. Did I do something wrong?
No.
Sorry, when people stare at my work, sometimes I get self-conscious.
I'm just like thinking, don't we know from there that it's not continuous because just crossing off the top and the bottom makes a hole in the graph?
Well, so here's the problem. If we're wanting to, at this point, we know it's not going to be continuous, but it's hard to use the definition because we don't know what, if anything, the limit as x approaches 3 of f of x is. So to justify your answer, we need to go ahead and look from the right also. So the limit as x approaches 3 from the right of f of x is the limit as x approaches 3 from the right of x squared minus 3, which is also 6. So what I would do, because I'm lazy, I would go back up to here and go, this is not equal to the limit as x approaches 3 of f of x, which was 6. Therefore, f is not continuous at x equals 3. So using this idea of continuity, we can actually define a removable discontinuity. All of you, I think, have a very good idea of what a removable discontinuity looks like, but we can define it in terms of limits. So let f be a function that is defined everywhere on an open interval containing c, except possibly at x equals c. So it doesn't have to be defined at c, but it's got to be defined everywhere else on both sides of c. C is a removable discontinuity of f if f is discontinuous at c, but the limit as x approaches c of f of x exists. The discontinuity may be removed by defining or redefining, if it's defined as something else, the value of f at c to be the limit as x approaches c of f of x. That's why it's called a removable discontinuity, because we can either just define, well, I want to fill that hole, or redefine, yeah, the thing that it was, I want to change it to something else. So, the floor function, and this is just another way to write the greatest integer function. I kind of like this better than intx. Your book uses intx, a lot of math books do, because the way that the brackets are, it's only got the ones on the bottom. That's to remind you, you go to the next lower one. You can also have a ceiling function, right? And so I like the way that this is written. So it's the greatest integer that is less than or equal to x. Determine if the floor function is continuous at x equals 1. Well, you guys know me. I'm a picture guy. All right, so the greatest integer function of 0 is 0 because it's less than or equal to. And as we move to the right, until we get to x equals 1, they're all going to be 0. And then we have this jump, because at 1, the value is 1, and that is going to continue until we get to 2. So is the floor function continuous at x equals 1?
No.
No. f of 1 is equal to 1. Again, I always start with the function. But what about the limit as x approaches 1 of f of x?
Zero. Doesn't exist.
Yeah, it doesn't exist. Therefore, f is not continuous at x equals 1. And when you're justifying continuity, you always want to talk about it in these terms. Does the function exist? Does the limit exist? Are they equal to each other? Those are the three things you need to look at. Now, we can also have something called one-sided continuity. Your book does some of this. I don't know that I've ever seen an AP problem on it, but it's an interesting thought experiment at least. So let f be a function defined on the interval from a to c. Notice that it's an open interval at a. So it doesn't have to be closed. It can be closed, but it could be open. Then f is continuous from the left at the number c if the limit as x approaches c from the left of f of x is equal to f of c. So like over here, well, I think we're gonna do that in just a second. Then let f be a function defined on the interval from c to b. So now we're going to values above c. F is continuous from the right at the number c if the limit as x approaches c from the right of f of x is equal to f of c. So the question here is the floor function continuous from the left or from the right at x equals 1? So let's go back up to here. So as we approach from the left, 1 is the function continuous from the left? Because f of 1 is way up here.
Yeah, you're right.
Is it continuous from the right?
So we have to say yeah.
Yeah, it's continuous from the right. So basically, it's like you're ignoring the other part of the graph entirely. So it's continuous from the right. And I want to look at this function real quickly. Is the function, which is the square root of 4 minus x squared, continuous on its domain? Functions like this one come up now and then. And this is a function that you probably haven't ever thought about what the graph of this looks like. But I wanted to do this now because it's going to come up again. So the function square root of 4 minus x squared. All right, first of all, let's talk about its domain. One of the nice things about this class is we never talk about imaginary numbers or complex numbers. Okay, there are other math classes that do calculus on those. I don't know anything about them other than, they exist. So if we're trying to keep this real, what stipulation do we need to have here? We're trying to avoid imaginary numbers.
Not be less than 0.
Right. The argument has to be greater than or equal to 0. So that's 4 minus x squared is greater than or equal to 0. So subtracting, we get 4 is greater than or equal to x squared. Or I really prefer the x on the left. I don't know about you, but if I just have the 1, it just makes me feel better when it's on the left. So x squared's got to be less than or equal to 4, which means that either one of two things has to be true. It's got to be in between what? -2 and +2? So that's going to be -2 is less than or equal to x is less than or equal to 2. Is this function defined everywhere in there? Yeah. And the value of the function and the value of the limit are going to be the same. So the answer to this is yes, but I also want you to look at the graph. I want you to know what this graph looks like the next time you see one like this. And before I just show you the graph, let me show you why it comes out this way. If y is equal to the square root of 4 minus x squared, notice that the domain is just x goes from -2 to +2, right? And y must be a positive number. So -2 is less than or equal to x is less than or equal to 2. And y is always positive or 0. Now I'm going to manipulate this into something that you're going to recognize. I'm going to square both sides. And that's the reason why it's important that you write out this part first, because when I square both sides, I lose this part about y's always got to be positive. So that's going to be y squared is equal to 4 minus x squared. Add x squared to both sides, and you've got x squared plus y squared is equal to 4. What is that? It's a circle. But this isn't a whole circle. Because it's the positive square root, it can only be a positive number for the y values. So this is the top half of a circle. If you want to graph the bottom half of the circle, all you got to do is slap a negative in front of the square root. Then it's the bottom half of the circle instead of the top half. And actually, I can remember teaching students on your calculator, if you want to graph a circle, the only way to do it on most calculators, and if you've got a TI, that includes you, is to graph the positive and negative square root. And even when you do that, it doesn't quite close up the sides very well. Which is one of the cool things. On the NumWorks calculator, you can graph conics. You could graph y as the square root of, you could graph x squared plus y squared equals 4, and it'll graph that, which is kind of nice. All right, any questions about this? All right. We need to get moving here. This class is over at 37 after. So a function is continuous on an open interval from a to b if it's continuous at every number in a to b. Right? A function is continuous on the interval that's closed at a but open at b if f is continuous on the open interval from a to b and continuous from the right at a. So this is letting us talk about continuity on a very limited domain. We can also do half open the other way, open at a, closed at b. And all of that goes to a function is continuous on the closed interval from a to b is if f is continuous on the open interval from a to b, continuous from the right at a, and continuous from the left at b. All of those things. So, continuity of a sum, difference, product, and quotient. If the functions f and g are continuous at c, and k is any real number, then the functions f plus g, f minus g, f times g, k times f are all continuous at c, no matter what. Provided that g of c is not equal to 0, the function f over g is also continuous at c. All right, so let's determine where this function is continuous. And it's actually easier to talk about, well, where is it not continuous? So for this part, it's just going to be a couple of points where it's not continuous. We've done this one a couple of times already today. So let's start with this one. For x minus 1, so h is continuous. Where? Well, we need the x minus 1 to be what?
Greater than or equal to 0.
Yeah, so x minus 1 needs to be greater than or equal to 0, which means that x is greater than or equal to 1. Except where? What does this part add in? Where is that not continuous that's in this interval? At x equals 2. So except at x equals 2. So sometimes it's easier to talk about where it's discontinuous. So a lot of times you talk about it's continuous everywhere except at, and that's what happens here. It's continuous on this interval except at x is 2. All right. Now, a super important idea. One that you probably already intuitively understand is the intermediate value theorem. So before we jump into what it says, I'm going to give you two examples that I think will explain the intermediate value theorem pretty well to you. So this morning when I left the house, it was 79 degrees. Okay? When I get home this afternoon, it's probably going to come down from the 100-something plus. Let's say it's 98 degrees when I get home. Do I know for certain, if I know those two things, that at some point today the temperature was 90 at my house?
Yeah.
Why?
Because it had to increase to get to 98.
Okay, because temperature is what kind of a function?
Linear.
No, no,
Wait, no.
it's not linear.
Good die. Agree with that.
Well, let me give you a different example and see if you can figure out why it's different. So I passed a gas station on the way in, and gas was, I've killed 3 already. Oh no, I've killed 2 already this morning of the mosquitoes. I think there's a colony back here. So I passed a gas station, and what does gas go for today these days?
$3.
So let's say that it was $2.89, and then on my way home today, It's $2.95. Did the price ever have to be $2.90?
Yes.
It couldn't just jump up?
Well, it could. It could.
Yeah, could they just jack the price up 6 cents a gallon?
That's true, yeah.
What's the difference between the price of gas as a function and temperature? It's what we're studying today.
Temperature's continuous.
Temperature is a continuous function. So if it goes from one value to another, it's got to go through all of the intermediate values. That's what this is called, the intermediate value theorem. On the other hand, the price of a gallon of gas is not constrained to be continuous, so it can jump all over the place. So the intermediate value theorem says, let f be a function that's continuous on the closed interval from a to b. If capital N is any number between f of a and f of b, then there is at least one number c in the open interval a to b such that f of c is equal to capital N. At some point, the function had to go through N. Could it go through multiple times? Absolutely. Right? In the temperature example, it may have gotten hot. We may have had a brief shower. The temperature goes down. It comes back up. Well, that's at least 3 times that it went through that. All right. So let's show that this polynomial function f of x, x cubed plus x squared minus x minus 2, must be equal to 5 at least once between x equals 1 and x equals 2. All right. So when you're showing this, you need to talk about what this says. So it says, let f be a continuous function. All right, so the first thing I need to say is f is continuous on the closed interval from 1 to 2 because it is a polynomial function. Sometimes people just say, oh, it's continuous, and I'm like, well, how do you know? A lot of times on the AP exam, they'll tell you this is a continuous function, right? They won't actually spell out the function in a lot of cases. All right, f of 1 is negative 1. And f of 2, let's see, that's 8, 12, 10 minus 2 is 8. And negative 1 is less than or equal to 5, which is less than or equal to 8. Therefore, and we usually just abbreviate this IVT, and then I would just write out all of this stuff up here. I'm not going to do it because we're out of time. I would just write all of that. Parroting back what they asked is frequently a good thing. All right, sorry we went a little bit long.